All right, let's take a look at one of the most important principles in chemical equilibrium. And this is going to explain how our original substance in the phenomena, the pink color and the one with the pink color and the purple color changed back and forth. So what we're going to be looking at today is systems that have reached an equilibrium. So as you learned from your reading in the last class, equilibrium occurs when the forward and the reverse reactions are happening at the same rate. So the overall ratio of reactants to products doesn't change at that point. Now, the reason that it's called dynamic equilibrium is because the reaction is still occurring. So it's just you have the reverse and the forward reaction that is occurring at the same rate, meaning the overall, again, meaning the overall ratio or balance of reactants to products is not changing. So you have the same molarity value of reactants and products. So once an equilibrium is established, though, it can be disrupted. And that's what we saw in the introductory phenomena. So the test tube that I had in the middle, the kind of the pinkish one, was that particular reaction at equilibrium. And then what I did is I manipulated two different parts. So as you guys saw, in the first part of the lab, I manipulated the temperature. And in the second part of the lab, I manipulated the amount of X, or the concentration that was in there. This then disrupts the equilibrium. It throws it off balance. So the system then needs to react to that. So what happens when a system is at equilibrium and you upset the balance? So this is governed by a man named Le Chatelier. So it's called Le Chatelier's principle. So he was a Frenchman that studied systems at equilibrium a couple hundred years ago. So he states that if a stress is applied to a system at equilibrium, the system shifts in the direction that relieves the stress. So chemical systems are just like you. If some sort of stress is placed on you, you're going to behave in a way that tries to alleviate that particular stress. So Le Chatelier's principle is used to predict how an equilibrium system will react to changes in concentration, pressure, and temperature. So notice here that we change pressure by changing the volume of something. So we saw this in the first semester, that pressure and volume go together. So in chemistry, our only real way to change pressure, or our main way to change pressure, is by changing the volume that a gas is under. So we can increase the amount of space that that gas occupies, or we can decrease it. And in response, the gas will change the pressure. So the easiest one to look at is changing concentration. So that's what I did in the second part of the experiment when I added X into it. So the first thing I did was add in the X, and what you saw is the test tube became really purple in color. So that was that particular equilibrium system responding to the addition of the X. In the second part of that, I added water. So water was also a part of the equilibrium system. And again, you saw a shift. So at the top there, it became clear. But had I been able to mix it, or had I spent the time to mix it, what you would have seen is it would have gone from purple back into the pinkish color. So if we add a reaction, or if we add a reactant, the forward reaction speeds up. So adding a reactant is going to want to, it's going to create a situation where that particular chemical system is looking to get rid of the reactant. You're dumping more on it. It wants to get rid of it. It was happy with the amount that it had, so it needs to get rid of it. The only way that it has to get rid of it is to turn it into product. So it starts speeding up. It starts to create more product. So that temporarily disrupts the equilibrium system. So over time, though, the forward reaction rate slows down and the reverse reaction rate speeds up. So once again, what you'll have is the system will regain its balance. So we'll regain an equilibrium amount. So at equilibrium, the forward and the reverse reactions occur at the same rate. So a new equilibrium position is established. So the only thing that changes here is that the overall molar quantities of both the reactants and the products go up. The actual ratio remains the same, though. So that's really important. And here, this is our K value. So this represents equilibrium. So because this K value represents the ratio of reactants to products. So because the overall ratio remains the same, our equilibrium constant remains unchanged. So we just spent a lot of time learning about ratios. So it doesn't matter what the numbers of the ratio are. What matters is the overall fundamental ratio. So a ratio of 1 to 2 is exactly the same as a ratio of 2 to 4, which is the same as a ratio of 3 to 6. The numbers themselves are different, but the fundamental ratio remains 1 to 2. And that's what's happened with this particular equilibrium system. So even though our quantity of reactants and products have gone up, the fundamental ratio remains unchanged, remains the same. So that's why it says here that the K value remains unchanged. So if we remove reactant, it's like you can think about a lake. So you have a reservoir, a certain water level, it's reached an equilibrium point, the water level is basically set. But if you dig a big hole in the bottom of the lake, if somehow you were able to get underneath the lake and you created a hole there, you'd have a bunch of water that would flow into that hole. So that's what happens here too. If you start to remove a reactant from a reaction, the reverse reaction speeds up. It's looking to fill the hole that was now created. So if you pull reactant out, the reverse reaction, the reverse reaction speeds up, meaning that what it does is it starts taking product and breaking it down into the original reactants that made the product. But once again, over time, the reverse reaction slows down and the forward reaction will speed up and a new equilibrium will be established. But just like the other one, the actual fundamental ratio of products to reactants remains the same. So our equilibrium constant also remains the same here. Changes in pressure. So the first thing to know with this is it only affects a gas. Changes in pressure do not affect any type of chemical system that is in a solid state or in a liquid state or in an aqueous state. It only affects gas. It only affects the substances in a gas state. So once again, these are easy to think about. You just have to ask yourself, if somebody did this to you, what would you do? So for a gas, if we decrease the volume, this is Boyle's law. If the volume goes down, pressure will go up. Volume and pressure are inversely proportional to each other. So volume goes down, pressure goes up. So what's happening is you're placing pressure on the system. That system is going to respond to alleviate that pressure. It wants to get rid of the pressure. So what it wants to do is have particles collide less frequently. It wants to create some space. So here's a diagram of that. So if we decrease the pressure here by moving the piston down, these molecules, gas molecules, now have less space to move in. That means they're going to hit each other more often. So they're going to hit each other in the walls more often. That's where pressure comes from. Because they're hitting more often, we're also going to end up with more energy. So we're going to end up with probably an increase in temperature along here as well. But I could talk about that. And so they're going to want to create some more space. They want to get the same amount of space between each of them as they had here. So what will it do to relieve that pressure? It will shift to the side with fewer moles of gas. So if we go back to the picture, it can't create more space. It can't push this piston up to create more space. So what it needs to do is get rid of some of these gas molecules. And it gets rid of these gas molecules by combining them with each other. So instead of two, like here, instead of two independent gas molecules, what it'll do is it'll stick these together. So now instead of two gas molecules, you only have one. So it's now doubled the space, so to speak, there. So this is the hardest of the reaction shifts. So you really have to pay attention. It's entirely based on how many moles of gas each side of the reaction has. So in this case, the forward reaction will speed up and over time, but again, over time, that forward reaction will slow down and the reverse reaction speeds up and a new equilibrium is established. But once again, the K value remains unchanged. Your ratio of products to reactants here also remains unchanged. It remains the same. So even though the numbers themselves, so the ratio, the actual digits, the numbers that make up the ratio will look different. If you divide them out, your fundamental ratio will be the same. So if a volume is decreased, concentrations of all gaseous substances increase. So the side with the fewer moles increases more. So that's not really that important. This is the big one right here though, changes in temperature. So this is what we saw in the first part of my lab there, my little lab video. So if you guys remember back to the first semester, change in H is change in enthalpy. If this is negative, it means energy is being given off. You have a reaction that's exothermic. So this means energy is being produced by the reaction. You would notice this by an increasing temperature. So heat is written as a product. So if H is positive now, this is an endothermic reaction. Energy is being absorbed, and heat would be written in as a reactant. So we're going to take a look at a couple examples of this in a minute. So here we have a reaction. So these back and forth arrows here indicate that this system will reach an equilibrium. So we have two gases here. First, we have one gas on the reactant side, and we see here we only have a single mole of this gas. On the product side, we see we have 2 moles of this particular gas. And if we look at the change of H value, it's positive 55.3 kilojoules. That means this is an endothermic reaction. It means that this particular reaction, the forward reaction, is going to need to absorb energy. You're going to have to heat it up in order to get this reaction to occur. So we're going to write energy in as a reactant. So see here, we just move it to the reactant side. So if we look at this, these two gases actually are different colors. This particular gas is a lighter color. This is a dark brown color. So here you can see the mix of gases at different temperatures. So if we see here at a cold temperature, we have a lot more of the N2O4 gas, because remember, this is a lighter color. That's because this is an endothermic reaction. If there's not enough heat here, this gas won't break apart into the NO2 gas. But as we start to increase the temperature, the reaction is now pushing to the right. So eventually at the boiling point of water at 100 degrees Celsius, we have a whole lot of this gas and not much of this anymore. So we've added energy here. So you can think of adding or subtracting energy just like adding or taking away a reactant or a product. So if we add energy, it's going to shift away from the side that has energy. If we take it away, it's going to shift towards that side. So again, Le Chatelier's principle is used to predict how an equilibrium system will react to changes in concentration, pressure, and temperature. So chemists can change conditions to make the reaction more productive. So that's the big thing here. So let's take a look at a couple of practice questions here. So here we go. Let's take a look at this practice question. So here's our reaction. So this says, question 1, if the temperature of the equilibrium system above increases. So what I always do to this to make it easier is I just go in, if something is being added or taken away, I just go and find it in the equation and I put an arrow next to it, an up or a down arrow. And then I push it. So here it says the temperature is increasing, so I find heat, and heat happens to be over here. So I'm going to put an up arrow over here. So remember, if we add something, it's going to push away. The reaction is going to want to get rid of it. So since heat is over here, the reaction is going to want to push in this direction. So what that means is this side is going to increase, and this side is going to decrease. So let's see which answer best describes that. So if the temperature of the equilibrium system above increases, we're going to get more of this side and less of this side momentarily. So N2 decreases. So if we look at N2, there it is. That's not right. So we can see there N2 is going to increase. H2 increases. So that's true. NH3 will decrease. So I find NH3 there. So that is true. So this is the correct answer. So there we go. Let's go down to the next one. So if the temperature of the equilibrium system above decreases, so again, now I'm going to find, here we're removing something from the equation. I'm going to find what's removed and put a down arrow. So in this case, we're taking heat out. So remember, in this case, if you remove something, it's like a hole in the bottom of a lake. Everything's going to flood to that side. So the reaction is going to flood over in this direction to try and replace what's being removed. So that means this side is going to increase, and this side will decrease. So I'm going to write that in. Again, I like writing this stuff in here. So let's see, N2 decreases. So far that's true. And NH3 increases. So there we go. So we didn't have to look any further. So that's that one. So let's see. Let's look at another question. Let's get another few reactions here. All right, so our next reaction is right there. So if the temperature of the above system increases, so again, temperature is increasing means we're adding energy. So there's my energy unit, kilojoules. So remember, that's the energy unit. So I'm going to put my up arrow. So once again, we're adding here, meaning we're going to shove it on this side. So I'm going to get an increase over here and a decrease over here. So let's see. So this side is going to decrease. So there's my substance there. So I'm just going to draw an arrow. So that guy decreases and CO there is going to increase. Okay. Here, it didn't tell you what the energy was. It just gave you the change of H. But here we see this is positive. So this is an endothermic reaction. So that means I'm going to come in here and add heat. So I'm going to add heat there. Okay. So now it says, which of the following is true about the above reaction if the temperature is raised? So once again, I find temperature. This, draw my up arrow, that means it's shoving this way. So I'm going to get an increase here. And this side then decreases. So which does that say? So equilibrium will shift to the right or to the left. So it will shift to the right. So again, which of the following is true about the reaction? The temperature's increase. So again, boink, there it goes. It's going to shove in this direction. So I'm going to get an increase in reactants and a decrease in products. And my answers got shoved off the bottom of the page on that one. So let's go down here. So in that case, equilibrium will shift to the left. So that one was the correct answer there. Let's take a look at something a bit different. We've done enough heat. So let's take a look at this one. So here's our reaction again. So it says the product is favored. So I want the reaction to shift in this direction. So there's a couple things we can do. We can add reactants. We can take out products. So that means we could either take this out or we could take heat out. So I could bring this down, I could bring this down, or I could increase over here. So let's see if any of those are an option. So when the reaction temperature is increased, so if I increase the temperature, it shifts in the opposite direction. So that's not it. When the volume of the reaction, ooh, here we have volume. So remember, in this case, when you see volume, what we're really talking about here is pressure. So this is a pressure question. When HE is added, so if I look at here, there's not even any HE in this, so that's irrelevant. When the reaction temperature is lowered. So when the reaction temperature is lowered. So there it is. If I lower the temperature, this is now going to be product favored. So there's our answer. Okay. So let's look at this one. One more. So which of the following is true about the above reaction when the pressure is increased by decreasing the volume? So remember, here, this is the toughest. Again, pressure goes up. It means that this favors fewer moles. Fewer moles of gas. So I want to find the side with fewer moles of gas. So this is where first you have to recognize exactly what substances are in the gas state. So this is in the gas state there. So here I have 1 mole on this side, and over here I have 2 moles. So if I increase pressure, it's going to favor fewer moles. It means it's going to shove this to the left. So equilibrium will shift to produce more of this. Okay, so this is what our lab is going to be over, is we're going to look at ways to manipulate a chemical reaction to try and learn something about it. So here's some practice questions just to give you a bit of a feel for it. All right, so that's good.